So welcome to Module 3, Part 1. So this week is going to be very similar to last week. We have two parts of the live lecture. The first part, we're really going to introduce the topic and go through some problems. The second part, we'll revisit it, go through a couple more problems, and then introduce another formula that you will have to know. But just stick with it. I know this week it's new material for most people. So remember that you've got to absorb it first and then apply it. And sometimes that takes a couple watches. Reviewing the live lecture more than once. There we go. We'll just go with that. So just keep in mind it's new. Module 2 and Module 3 are pretty tough because it's a lot of new ideas, but just stick with it. And remember, if you have questions, you can always reach out to me. Okay, so what we're going to talk about today is we're actually going to introduce a new distribution. So last week we talked about the normal distribution, right? The beautiful symmetrical curve that we love so much. And we did things like find the probability, which is the area underneath the curve. And we did that using the norm.dist function. We also found like your z-values. So on that number line where the z-value is. Well, we're going to keep those ideas. We're just going to use a different distribution, which looks very similar, called the t distribution. So don't freak out because it's like a whole new distribution. It's very similar to the normal distribution, okay? And we're going to use the same concepts as last week. We're also going to talk about a few more vocab words. I know there's a lot in statistics, but just stick with it. Remember to write it down. Interpret it how you understand it as well. So we're going to talk about population parameters and point estimates. And then we're going to get to the heart of the matter, which is actually calculating confidence intervals. And these are just ranges of values that are possible for our mean. And we'll get into that in a little more detail as well. A lot more detail. So in Module 2, we discussed the normal distribution. This should look familiar to everybody. We had the mean in the middle, right? Your mean was in the middle, and then your standard deviation was how many steps away you were going from the mean. Now, when we use that variable x, we were talking about the normal distribution, where your mean could be any number, and your standard deviation could be any number. But we also talked about our z variable. And if you remember, our z variable was our standard normal variable. Now remember, with the standard normal, what was our mean? Our mean was 0. And then our standard deviation was 1. Yes, very good. Awesome. I love that you guys remember this stuff. Perfect. So your standard normal was special, hence standard. So that was our z. Now, we're going to work with and introduce the t distribution. So we got a new variable here called t. Now notice that the t distribution has that bell-shaped curve where it's even and it's symmetrical. You've got the mean in the middle and you've got your standard deviation on both sides. And the only thing that's different about the t distribution is that how tall or how short it is simply depends on your sample size. Now, sample size is how many people you're looking at in a sample or how many people you survey. So, for example, if I was looking at my students' ages, okay, the number of students I have in statistics, I think I have about, we'll just say an even 200. So that would be my sample size. How many people I'm interviewing would be that 200, okay? So the layout of the distribution depends on the sample size, as I said. Now be careful because, again, we're introducing those variables. Remember, I mentioned variables are super important. Hopefully you've got that note card that we talked about before and you're writing them down. Sample size is going to be represented as n. So for my students in this class, my n would be equal to 200 because that's the number of students in my class that I'm surveying. Now, the reason why we need to use this t-distribution is when we are placed in certain situations. So what are those certain situations? The first one is that you have a small sample, and this is usually less than 30, okay? 30 is like a magical number in stats, but we don't really need to worry about that one. The whole reason we're going to use the t-distribution is because we don't know the population standard deviation. Okay, so remember this little sigma guy? He means population standard deviation. So we're going to use him, the t-distribution, when we don't know the population standard deviation, or the standard deviation as it applies to everybody in the population. So if I were to do a survey, I wouldn't know what the average age of all students at Rasmussen was, right? So I wouldn't be able to use the z, the normal distribution. I'd have to use my t-distribution because all I could do is have my little sample of 200 students. So that's why I would have to use my t-distribution. I don't know the population standard deviation. So just like for the normal distribution, we have functions in Excel to help us calculate. Yay, Excel! So we are actually going to use the t.dist function. So it's very similar to the norm distribution, except it's going to be t.dist, okay? T-distribution. And the first number you're going to put in there is your t value, right? Just like your x or your z number that we worked with before. The second number is actually going to be your degrees of freedom. That df stands for degrees of freedom. I think I actually, nope, I did not put it on here, so let me write it on here. Degrees of freedom, which is just your sample size, n, minus 1. So for my students, right, we talked about 200 students, my degrees of freedom would be 200 minus 1, or 199, right? So that would be my degrees of freedom. So you're just taking 1 away from your sample size. And then, of course, our favorite word, true. Now remember that this only works for a left-handed value. For so if you're trying to find the probability that t is less than some number, I don't know what it is, okay, 5 or something like that, you would use this function. Okay. Now last week we also talked about how to find the z value when you're given a probability. All right, we're given a probability. We have to find the z function. I think that was problem 5. Do you guys remember problem 5 on the deliverable last week? Where you had to find the z value. You were given a probability. You had to come back with the z value. We can do the same thing with your t value, where instead of using norm.in inverse, we're using t.inverse. And you're putting in the probability and then comma degrees of freedom. So df stands for degrees of freedom. Now remember, this is for a left-handed, left-tailed value as well, which is a less than value as well. And we worked with that last week a lot, okay? And we're going to revisit that when we talk about how to actually use it. That's just a little foreshadow and hopefully connecting you to last week so you see those connections and hopefully see that we're not learning completely new stuff. There's some new stuff, but we're building on the old, okay? Now, another vocab word that we need to talk about today is called a population parameter. So a little alliteration there, PP. Population parameter is any summary number such as an average or a mean or a percentage or standard deviation or variance, whatever that summary number is, okay, as it applies to the entire population. Okay, so that's going to be a population parameter. So these are things like your mu, which is your population mean. This is also your sigma, which is your population standard deviation. These are all population parameters. The name kind of gives it away, right? Population, these are the population parameters. So, for example, one population parameter is mu, which represents the population mean. We talked about that. What are the variables that we've discussed so far that represent population, in other words? Now, the problem with finding population parameters is that oftentimes we don't know what the number is that applies to the entire population. It's very hard to survey every single person in a population, right? Think of me trying to get surveys back from every single Rasmussen student. I'm sure you can imagine how difficult that is. It's very, very difficult. You don't want to respond. You have other things to do. So unless we have like a census, which they do every 10 years, right? They go around to everybody, all the houses, and they gather information. You usually don't have population parameters, right? So what they do instead is they estimate what it is based on a sample. So they take a sample of the group, they find out the what we call point estimate, or sometimes it's called a sample statistic. Okay, we're going to call it point estimate though. And a point estimate is a value that you get from a sample. Okay, so a value you come up with from a sample, whether that's the mean of the sample, the standard deviation of the sample, or the variance of the sample, whatever it is, that's going to be your point estimate. And what we're going to do is we're going to use that point estimate to estimate the population parameter. So we're going to use that sample and apply it to the population. So my example for that is the sample mean x bar. We're talking about a sample here. That would be your point estimate, would be x bar, is the best point estimate for the population parameter mu. So what you're doing is you're finding the average or the mean of that sample, average age of my students, and I'm going to take that average age of my students and apply it to the entire population. So the entire world of Rasmussen. Now, here's a little visual. I know it's a little blurry, but I really liked the visual. So, okay, so let's say this is the population that we're trying to get information about. Maybe it's all the students at Rasmussen. That's all the population. We want to know the population mean. So this would be my population parameter, mu. That's the population mean. Well, we can't just jump to that conclusion. What we have to do is we have to take a sample, so a smaller group of people from the population, so maybe my class, for example, and we're going to make conclusions from that sample that we took. So we do our little work, we do Excel, gather information, do our little Excel. We get to x bar, which is our sample mean or statistic, or you could also call it your point estimate. Same thing, okay? You gather this information, you do the calculations, you find your point estimate of x bar. Then what you're going to do is you're going to use inference, which is drawing conclusions, to take that x bar to mu. So you're going to jump to conclusions. That always reminds me of Office Space, the jump to conclusions map. I don't know if you've ever seen it, but basically you're taking x bar and you are translating it to the population mean. So we can make conclusions about the population based on a sample. I hope that visual kind of helps put that together a little bit more. Sometimes visualizing things can help. Okay, so another quick thing that I wanted to show you. So here are some population parameters. We just call them parameters, but sometimes if you put population in front of there, it gets stuck in your head that that represents population. So for the population mean, you would have mu, right? We worked with that before. Population standard deviation, we have sigma. We've worked with that before. The only one we haven't worked with is for a proportion, which is like P. So a proportion is basically like if I was to say what proportion of my students have kids, it'd probably be something like 80% of my students. So a proportion is just a percent, basically something like that. How many students have kids? 80%. That would be a proportion population parameter. We haven't really worked with it before, but we will be kind of talking about it a little bit later on, so that's why I wanted to bring it up and introduce it. Now, sample statistics or point estimates are for the samples. You can see P hat. We call that P hat. It's kind of funny because it looks like it's a P with a little hat on it. Do you guys see it now? It's like a party hat. Woohoo! No, just me. And basically that's just the proportion of the sample that you took. So a little P hat. The next one is X bar. You're probably pretty familiar with that one. It has an X with a bar over it, and that's for your sample mean. And then S is your sample standard deviation. Are a lot of these looking familiar? Like, okay. Standard deviation. I don't know what I was typing there. Deviation. P should really only be the new variable that you haven't really seen. P and P hat. We haven't talked about those before, but it's always good to introduce them before we get to them. Okay, any questions on parameter statistic? So it's just for population and sample. Just differentiating the two. Okay, so now that gets us into the meat of and potatoes of today, which is about confidence interval. So a confidence interval gives us a range of values that we can be sure that a population parameter falls into. So what does that mean? So let's take the example that I'm trying to find the average age, the mean of my students. Well, I'm going to go ahead and survey my 200 students, right, and find the average age. The average age, X bar, average age or whatever, is going to be my point estimate. It's going to be my point estimate for that sample. And what I'm going to do is I'm going to take that average age. Let's say I find the average age is 28, okay, 28 years old. That's my guess, okay? I'm going to say I want to apply that to my entire population, but I can't just say, oh, that means everybody at Rasmussen, the average age is 28. Can I? I don't know that because I haven't surveyed everybody in the population, just my little class. So what I have to do is I have to construct this confidence interval to be able to be sure that my actual mean age is within a certain range. So perhaps the average age for Rasmussen students is between 25 and 31. Maybe it's between there. And I can be 95% sure that it is a value in between there. That's really what we're doing here. So we're going to construct intervals that lets us be pretty sure that the population parameter we're trying to find is within those values, such as the average age of students that we're trying to find. So why do we need confidence intervals? Well, we need to be able to, I totally blanked on this one, but we need to be able to give ranges for value because we don't know exactly what that value is because we can't survey the entire population. So we need to take that sample and be pretty sure that we can apply it to the entire population. It's really what we're doing with confidence intervals. We're taking a sample and translating it to the entire population. That's pretty much what we're doing here. Okay. So basically you're going to have like a lower limit, which is the smaller value. So maybe average age, what did I pick, 25 or something? That would be my lower limit. And then my upper limit would be, what, I think I said 31. I think that was it. Those would be my limits of the confidence interval, and that means my population parameter can be anywhere between there. So that kind of just gives you an idea of confidence intervals. We're trying to find two values, and we're trying to be 95% sure, or have a probability of 95% that the values fall between two values here, whatever those two values are. So when we're constructing a confidence interval, it's going to consist of three parts. The first part is the confidence level. Now the confidence level is how confident are you? Now we like to stick to about 90%, 95%, or 99% sure. There's really no way that you can be 100% sure unless you actually survey the entire population. It's not possible, right? You can't be 100% sure unless it's actually raining. Same idea here. You've got to do the entire population to be 100% sure. So we stick to about 95%, 99% for confidence levels. You also need to come up with your statistic or what we call our point estimate. That was what I surveyed when I did my survey of you guys, my imaginary survey, and I found that average age statistic. That would be my point estimate because that's what I got from my sample, not what I'm going to apply to the entire, and then I need to apply it to the entire population. Okay. And then I also need to calculate my margin of error. Now, margin of error is calculated using a formula, which we will talk about in a second. It can get a little tricky, so just make sure you've got your Excel out, you're ready to go, and you're going to work through those margin of errors as well. Okay. And the margin of error, I should specify. Margin of error is how much error you are allowed. So in general, the amount of error you're allowed is this area on either side of the confidence interval. So if you have to be 95% sure, that means you have a 5% margin of error. And the reason for that is you just take 100 minus 95. And you get 5% left over, right? So you have 5% margin of error. Likewise, if we turn that confidence level up to 99%, now your margin of error has gone down to just 1%, right? 100 minus 99, just 1%. That needs to be split between those two sides. So margin of error tells you how sure you actually are of that value. Now, I guess I went into these things too soon, but anyways, let's revisit them. So confidence level, as I said, describes the likelihood that a particular sampling method will produce a confidence interval that includes the true population parameter. So basically, we're just saying how sure are we that that value is somewhere in between those two numbers. So how sure are we that the actual average age of Rasmussen students is between, I should really write these numbers down, but I think I said 26 to 31. Are we 90% sure? Are we 95% sure? Are we 99% sure? Those will be our confidence levels that we will work with. You don't really want to go below 90%. That seems kind of worthless after a while. So stick above 90. Now, in a confidence interval, the range of values, as we talked about below, is the margin of error. So if you are 90% sure, your margin of error would be 10%, right? 100 minus 90 is 10%. So here we have our point estimate in the middle, point estimate. And what we're doing is we're going to either add the margin of error to get a larger number, or the upper limit. Let's write that, upper limit. Or we're going to take our point estimate, which is our sample mean or whatever it is, and we're going to subtract that margin of error to get the lower limit. And that will give us our confidence interval, or how sure are we that our value actually lies between those 2 points. Okay. So for our purposes and on your homework, we're going to stick with estimating the population parameter of the population mean mu. We're going to stick with that one. So we're going to be trying to take our x bar, and apply it to the population mean mu. So how do we do that? Well, we need to find the confidence interval. How do we do that? Well, what you're going to do, as we talked about before, is you're going to take mu. Okay, plop it in the middle of these inequalities, so it's going to give you an interval. And on the left-hand side, you have your lower limit, which is your x bar, your sample mean, minus your margin of error, just like we talked about before. And then on the upper limit, we're going to take our x bar, our sample mean, and we're going to add our margin of error. So basically what we're doing here is we're just taking our sample mean and we're either adding the margin of error or subtracting it to get that interval. Okay, so depending if your population standard deviation is known or not, you will either have to use a z or t-score. Now, we talked about when t is used. T is used when you do not know the standard deviation. That is what we're mostly going to use. And in fact, that's what you're going to use on your homework because we won't know our population standard deviation. So when your population standard deviation is unknown, so when you only know your sample, we use the following method to calculate the margin of error. So let's break this down. The margin of error is E, margin of error, equals T of alpha over 2. Don't get hung up on that right now. That's going to turn into a number. That's your T statistic, or your T number, just like if it was a Z number on that number line, you're just finding that number line, times your sample standard deviation, S, divided by the square root of n. Now, does anybody remember what n stands for? I don't know if anybody remembers this. Yay, perfect. It's your sample size. Yeah. How many people are you interviewing? Remember in the beginning when I said your variables are going to come back a lot? They really are. So that's why I'm trying to practice them and get you guys set up to be strong in this part. Okay, and then we talked about this before. The degrees of freedom is n minus 1. So when you're calculating the degrees of freedom, you're going to take your sample size and you're just going to subtract 1. So my sample size was 200. I'd subtract 1 and get 199. Okay, so this was all the theoretical talk. We really want to get into, oh wait, we're still theoretically talking a little bit longer. Okay, and then we'll get into practice problems. Just stick with me. Just stick with it, okay? So let's talk about how to find your critical value. Okay, I shouldn't call that your T, well, it is your T statistic, but let's call that our critical value instead. So erase that and write critical value. That's more appropriate to call that. So T of alpha over 2 is going to be our critical value. To find that, you have to know your degrees of freedom, which we talked about before was your sample size minus 1. You also have to compute alpha. Now, I'm going to quickly compute alpha for a couple values. So 95%, alpha is going to be 1 minus 0.95. So just 1 minus, change that to a decimal, which is going to be, so alpha would be 0.05. So if you had a 95% confidence interval, CI, that would turn into an alpha of 0.05. And alpha is your margin of error, 5% margin of error, basically. Okay, how about a 99% confidence interval? Does anybody think they know what the alpha would be? What would your alpha? Oh, I didn't mention this. This looks like an A. Looks kind of like a fishy. Well, A fishy, that's alpha. So that's alpha. So if our confidence interval is 99%, we would take 1 minus 0.99. So that would mean our alpha is 0.01. Yes, very good. Awesome. And one last one that I do want to do is 90% confidence interval. Okay, so does anyone think they know what the alpha is for a 90% confidence interval? The nice thing is once you do this, you do not have to repeat it. Okay, you'll have that as like a little go-to. Good, yes. 1 minus 0.90, which is 0.10 or 0.1, whatever you want to do it as. Now, oh, I'm going to move these. Hold on. Okay. There we go. Get it out of the way. Now, when we're looking, remember, this is your confidence interval from this point to this point, right? So your margin of error, so let's say you're like 95% sure, right? Well, you have two tails. We call this two tails on either side. That's where your margin of error can lie. So you have to split that 5% between two values. So that's why they call it alpha over 2. You're splitting your values into 2, your margin of error into 2 values, T of alpha over 2. Don't get too hung up on that. I'm going to be honest with you. You guys will not have to know that. All you will have to know is to find the critical value, T of alpha over 2. You need to use the function T dot inverse. So that inverse function gives you the T value. But you need to use the specific dot 2T. And the 2T says that there's 2 tails because your margin of error could lie on either side of that confidence interval. Can lie on either side of that confidence interval. So equals T dot inverse dot 2T. And then inside you're going to have your alpha, which we calculated over here. You see all your alphas right here. We'll highlight them. Boom, ba-doom, boom, ba-doom. Okay. So we have all those alphas. That's what you're going to put in. And then comma degrees of freedom. Degrees of freedom are n minus 1. So let's go ahead and practice that because we're trying to get used to it. Okay. It says find the critical value, T of alpha over 2, corresponding to a 95% confidence level, given that the sample size has n equals 15. So there's 15 people that you surveyed or 15 samples that you looked at. So the first thing that we need to do is we're trying to find T of alpha over 2. We're trying to find that critical value. So let's go ahead and calculate the degrees of freedom. Does anyone know what the degrees of freedom would be? Anyone want to take a stab at that? So degrees of freedom is n minus 1. Very good, n minus 1. So since my n is 15, I'm just going to go ahead and take 15 minus 1, which is 14. It's going to be my degrees of freedom. You don't really have to write it out. You can do it in your head if you want to. But for the sake of notes, you probably want to have it all written out. Okay. Now, the next thing that we need to do is find our alpha, our compute our alpha, our margin of error type thing. Okay. So alpha depends on the confidence level. So when the confidence level is 95%, what's our alpha going to be? So here's our confidence interval, 95%. 1 minus 0.95 is going to be 0.05. Just go grab it. We already did the calculations. You don't have to worry about those. Okay, great. Now that we have those two values, our alpha and our degrees of freedom, we can plug it into our formula. So we're going to type in T dot inverse dot 2T, because it's two-tailed on both sides. Alpha is going to be 0.05. My degrees of freedom are going to be 14. Now, could you do that all in one step? You sure could, but take it step by step, especially when you're starting out, okay? So we're going to open up our Excel to do some calculations. So this is going to be our T critical value. Let's just call it critical value. Okay. So equals T dot inverse. Now notice there's a T dot inverse and a T dot inverse dot 2T. You always want to do the 2T because you have to get both tails. Both sides. Not one-sided here. And then I type in 0.05 for the alpha and 14 for my n, and I get 2.14. 2.14. Now, let me revisit the rounding there. 2.14. That's going to be my T of alpha over 2. That's going to be my critical value. Now, remember that when we talked about our z-scores, we thought about the curve, and our z-scores were down here by the mean. So this was 0, and then our values here. Same thing, but instead of a z, we're going to have a t. Okay, so my t-scores, my t of alpha over 2, are going to be a positive 2.14, and then also a negative 2.14, because it's two-tail. So, and then this would be my 95% confidence interval. So that would be how I would come up with the critical value. And I'm going to use that critical value to determine the margin of error. So it's kind of like a couple step process here. So just stick with it and we'll walk through it in totality. So make sure you're taking good notes when we go through those problems. Okay, so 900 high school freshmen were randomly selected for a national survey. Among survey participants, the mean grade point average, GPA, was 2.7, and the standard deviation was 0.4. What is the margin of error, assuming a 95% confidence interval? So notice what they did here is they took a survey, okay, of a group of students, and they surveyed 900 students, okay? And they found the mean grade point average of that sample was 2.7. And of that sample, the standard deviation was 0.4. So notice here we're working with all sample information. We don't know what the population information is, just for this sample. So we're going to use our sample variables. So sample standard deviation is going to be, anybody know? S? Okay. How about sample mean? That 2.7, that sample mean. X bar. X bar is our sample mean. And then, very good, awesome. I know it's kind of hard to be like, I can't type this on my, in the notes here, but how about 900? What variable is going to represent 900? How many students we surveyed? What variable is going to, very good, yes, N. N is your sample size. So I'm going to go ahead and write N there for 900. Now, all they want us to do is find the margin of error. I know you're like, that's it? No, I'm just kidding. Margin of error formula I wrote down here, but let's go ahead and rewrite it for good measure. Equals T of alpha over 2 times S divided by the square root of N. Now, when we're looking at this, to find the margin of error, we have the sample standard deviation. They told us it was 0.04. We also have our N value, the number of students, 900. But we don't have the critical value. So we need to actually find the critical value first. So that's what we're going to do. We're going to find the critical value of T of alpha over 2 first. So to find the critical value, we need to first find your degrees of freedom. What's our degrees of freedom here? Anybody know? Great. Yep, you're going to take, it's N minus 1. So our N is 900. So it's 900 minus 1, which is 899. And then what we need next is we need our alpha. What's our alpha? So it depends on our confidence level. Since we have a 95% confidence level, our alpha, if we go back to our chart here, which is awesome, you may want to write that down on a note card, wink wink, is 0.05. Now we can actually do our calculations. So we do the T dot inverse dot 2T. I don't know why I made that small. And our alpha goes first. And our degrees of freedom go second. So go ahead and plug that in and let me know what you come up with for your T. So our critical value, 1.96. So T dot inverse dot 2T, that sounds right. Let's just double check here. 899. Oops, get the right one. There we go. Double check it looks correct. 1.96. Now I'm rounding these to 2 decimal places because we're talking about on the number line. And this is not probability. This is a number on the number line like we were talking about before. Like we talked about the z-scores. The t-scores, again, are numbers on the number line. So 1.96. 1.96. And that's going to represent your T of alpha over 2, which we call our critical value. So now that we have that T of alpha over 2, we can use our margin of error and find our margin of error. So to do that, let's plug it in. So E equals T of alpha over 2 is 1.96 times our S is our sample standard deviation, which they gave us 0.04, or 0.4, excuse me. And then we're going to divide that by the square root of N. Our N is 900. So I want to show you how to type this in your Excel sheet using reference cells. So let's talk about what that means. So we're going to find our E, our margin of error. Okay. So we're going to go equals. Now instead of typing in 1.96, since I've already calculated my critical value above, I'm just going to click on that, and it's going to use the value in there as a reference, hence the name reference cell. So see how it highlights B3 to show you I'm going to use the number that's in that cell. And we're going to multiply by 0.4 and then divide by the square root of n. So how do we type in the square root of 900? It's SQRT. That's square root, SQRT. And then in parentheses, you'll put your number. So I'll leave that up there for a second so you can write that down. So if you're ever trying to find the square root, it's SQRT, and then in parentheses, you'll put the number. Hit enter. And it actually looks like a pretty small number. It's 0.026. 0.026. It's safe to round to 3 decimal places for the margin of error. Because remember, we'll use that reference cell when we get to confidence intervals. So it was 0.026. Basically what that means is if the GPA for our sample was 2.7, that was, ooh, do not use that color. Let me show you visually. 2.7 was our sample mean, which was also our point estimate. And what our margin of error of 0.026 does, it says I need to either add 0.026 or I need to subtract that to get my range of possible values. And that's what we're going to do in the next step. So the margin of error tells you how much you should add or subtract to that point estimate, that sample mean that you calculated. And then that will allow you to apply it to the entire population mean. Okay, so let's take everything that we've learned so far and put it together. So far we learned how to calculate the critical value. We learned how to take that and find the margin of error. Now I want to take that and actually calculate the confidence interval. So we're going to do these in steps. So make sure you're following those steps as you're going through the problems. So suppose you work for the Department of Natural Resources and you want to estimate with a 95% confidence the mean or the average length of all walleye fingerlings in a fish hatchery pond. Maybe you're a scientist, okay, just go with it. You take a random sample of 10 fingerlings and determine that the average length is 7.5 inches. And the sample standard deviation is 2.3 inches. So the first thing I like to note here is that we're working with a sample. Notice that in this situation, it's all working with a sample. There's no population assumptions going on, okay? We just have a sample. And they want us to come up with a confidence interval, a 95% confidence interval. 95, oh, you cannot see that. Let's use a different color here. I want to be 95% sure what the mean length is going to be of these fish. So your random sample is 10 fingerlings. What variable is that 10 going to be replaced with? What do you guys think? What's the 10 represent? Awesome. Yes, it's going to be your N. 10 is your sample size, how many fish you're looking at. Okay, the next number I see is 7.5 inches. Now, what variable is that going to represent? Remember, we're working with a sample. Great. So your average, so we see average length. So average is the same as a mean. And since we're working in sample mean, we're going to use X bar. Or you could write it out X dash bar. We try to use the symbols though when we're writing. Just a little easier. Okay, and then the final number we see here is 2.3 inches. So what variable represents that one? What do we think? So that's going to be your sample standard deviation, which will be S. Yeah. We're practicing using these variables, so if you don't quite get it yet, make sure you've got that note card with what they represent and make sure you're practicing them on your own. This is going to help you understand those concepts. Okay, so let's go ahead and walk through how to make a confidence interval. So the first thing you need is your critical value. We did this last time, but let's walk through that again. So we're trying to come up with our critical value first. So the first part of coming up with a critical value is, if we remember we did it last time, finding the degrees of freedom. So can anyone tell me what the degrees of freedom here are? Lori, I love that you gave me an equation. You're absolutely correct. Remember, it's n minus 1. So that would be 10 minus 1 or 9. Okay. The next thing we need to do is alpha. Can anyone tell me what alpha is based on the fact that you need a 95% confidence level? To be 95% sure. So what does that mean for our alpha? Yeah, we use 95% sure a lot, if you noticed. So that means our alpha is 0.05. Then last but not least, we need to take these values and plug them into Excel. So our T of alpha over 2 is going to be calculated by typing in Excel. T dot inverse dot 2t. And inside you need to do your alpha first, 0.05, and then comma your degrees of freedom. So we need to figure out what is our T of alpha over 2. So we're going to go ahead and pull up our wonderful, and I'm going to scroll down because I want to put these all the same. So we're coming up with our critical value equals T dot inverse dot 2t in parentheses 0.05 comma 9. Hit enter, and we do get 2.26. So that's our T of alpha over 2. 2.26. Is that what everybody came up with when they calculated that? 2.26? Yes? Okay. Wonderful. Now, we did our first step, finding the critical value. Our second step, so I'm going to make a little space here. We need to come up with our margin of error. So luckily, I don't know how to spell error anymore, apparently. Margin of error. Our formula is down there. Boom. E equals T of alpha over 2 times S divided by square root of n. So the first thing we need to do, just plug in our values. So what is our T of alpha over 2? It's what we just found, 2.26. What is our S? Well, luckily we've already labeled that. That's our sample standard deviation of 2.3. Then we're going to divide that by the square root of n. Now, we've already said our n is 10, so I'm just going to plug that into the square root. Now, I'm going to go ahead and plug this into Excel using those reference points. So Here we're coming up with our margin of error. So equals, now I'm going to use my reference cell again. So my critical value is right above. So I'm just going to click on it. It shows me B8 is the value I'm using. Multiply that by 2.3. That's my sample standard deviation. And divide it by square root. How do we type in square root again? SQRT. And then plug in 10. So we're taking the square root of 10 there on the denominator. Hit enter, and it looks like our margin of error is 1.645. 1.645. Is that what everybody got? 1.645. That's our E. That's our E value. Okay, I see a yes. Excellent. There is one last step. There's only 3 steps. You're like, only 3? Are you sure? I promise there's only 3 steps. So the last step is we do need to come up with a confidence interval. And I'm seeing that I'm running out of space. But this is where we're trying to come up with that lower bound and upper bound. So we're trying to find our values, or our possible values of our population mean. And to do that, what we're going to do is we're going to take our X bar, and our X bar is 7.5, and we're going to subtract our margin of error. Our margin of error is 1.645. Boop. That's going to be our lower limit. Okay. The other side of our population mean, we're going to take our X bar, which again is 7.5, and we're going to add our margin of error, 1.645. This is going to be our upper limit. Let me show you how to do that quickly on Excel. We are going to use reference cells again because we want to avoid rounding as much as possible until the very end. I know we rounded to write them on the slide, but honestly, I was not going to write out the whole entire number. Just takes a bit too long. So lower limit is what we're going to calculate first. So we're going to take X bar, so equals, that's what triggers the calculation, right? 7.5. And we're going to subtract our margin of error. So instead of typing in 1.645, I'm just going to click on my margin of error cell, which is B9 for me. Hit enter. So that means my lower limit is 5.85. What's my upper limit? Let's calculate it. So 7.5, and we're going to add my margin of error. So again, I'm going to click my margin of error cell, double check that it looks correct, hit enter. 9.1, I think that's what you said up there. Yes, Ashley is correct. 9.1 would be our upper limit. So let me write that down real quick. So our lower limit was 5.85. And our upper limit was 9.15. Let's round that 4 up to a 5 since the next number is 5. And let's talk about what that means, because it's always about bringing it back to what does this actually mean. So I ran out of space down there, so I'm going to quickly write it up here. That means our population mean, our population parameter here, is going to be between either 5.85 inches. Okay, so the average length of these fish for the population should be between 5.85 inches and 9.15 inches. So it gives you a range of possible values. such that we can be 95% sure that the actual average of these fish is somewhere between those two values. Now, as you can see, these values are pretty spread out, like 5 inches to 9 inches. That seems like it's pretty spread out. And that's simply because our sample size, if you look, we only looked at 10 fish, okay? That is not very many, right? I'm sure you can all agree. That's a low sample space. You'd be like, let's sample a few more fish than that. So the more you sample, the closer your numbers will get. So just keep that in mind. Because the more people you sample, the closer you're going to get to the actual population parameter. Now we are at 60 minutes. I did have one more example. But I'm going to go ahead and talk about the homework now. I will do this problem tomorrow, on our live lecture tomorrow. I'm going to go ahead and pull up the homework though and talk about it. So here is our deliverable 3, confidence interval. So we are back to the information that we worked with on deliverable 1, where you had that worksheet and you were looking at the salary distributions of jobs in Minnesota that range from $40,000 to $120,000 per year. And you have this spreadsheet that we worked with before, so you're going to get that spreadsheet and you're going to do your calculations in it. Just as a reminder, you need to turn in both the Word document and the Excel sheet. Please make sure you're turning in both. I probably have emailed you if you have not, so you know. Yeah. I think I didn't make that abundantly clear. Like I mentioned it last week, but I didn't hammer it home. So I'm trying to make sure I hammer it home. In fact, every single deliverable you can expect to turn in either a worksheet or a PowerPoint and an Excel sheet. An Excel sheet will always be turned in as well. So anyways, so we download the worksheet. Looks like this. Yay, deliverable 3. And it says, discuss the importance of constructing confidence intervals for the population mean. So it's only looking at the population mean by answering these questions. What are confidence intervals? What is the point estimate? What is the best point estimate for the population mean? Explain, and why do we need confidence intervals? Now, if you've watched the live lecture and you're still a little shaky on these, go read the book. Go look at our information. Go to Google and try to read more information. Go to YouTube and go confidence intervals. And, you know, sometimes it helps to have someone else explain these ideas. Sometimes I try to caution that because if you get too many voices in your head, it can cause confusion. That's the only reason I tend to caution it. But if you're completely lost, please find someone else. Maybe Khan Academy. That's a great resource. But take a couple of different and see the interconnecting ideas that go through this. But this must be in your own words. So make sure you're saying what are confidence intervals in your own words. Obviously, you can base it off of what we have in our notes. But why do you need confidence intervals? That's definitely going to be in your own words because I didn't really give that directly to you. So number 2, using the data from the Excel workbook, so the one you downloaded, construct a 95% confidence interval for the population mean. Assume that your data is normally distributed and your population standard deviation is unknown. You don't know what it is. Include a statement that correctly interprets the confidence interval in context to the scenario. Hint. This is an important hint. You've calculated the sample mean and the sample standard deviation before. You did it in deliverable 1. So you're going to use information from deliverable 1 to help you here. Wink, wink, wink. Grab that deliverable 1, have it open. Maybe even use the Excel document from deliverable 1 to help you go along. Or you can recalculate the mean and the standard deviation if you want to. Up to you. So number 2, you're going to be constructing that 95% confidence interval like we did here. So that confidence interval here that we talked about. And then you're going to show So my suggestion is to show all your steps. If you need to make this larger, if this box is not large enough, feel free to grab that tab and just expand it. Feel free. You can use the whole page length, whatever you need, okay, to do that problem. You know, maybe break it into those steps that we did. Critical value first, then find your margin of error, then find your confidence interval, and then interpret your confidence interval for the problem, right? We talked about what this means for those fish. What do we interpret those links for the fish? Okay. Number 3, we haven't exactly done this problem yet, but it's the same type of idea. The only thing that's different is that we have a 99% confidence interval that we're trying to do instead here. And you could start on that. We've talked about everything you need to know, but we will be doing a problem like that. And then number 4, we haven't really talked about that, but you can research it and look into that a little bit more if you want to. Why are some confidence intervals wider, and what's the reason for that? Okay. Particularly, why is a 99% confidence interval wider? You can probably do some research on that and kind of get an idea. Number 5, do not do number 5 until we talk about, until we watch part 2. Okay, go through part 2 because we have not talked about the formula yet. We have not talked about that. Do not try that yet. Okay, so you could get started on this. Maybe, I would say maybe try 2 and then go on to part 2 and watch that tomorrow. So that'll be on Tuesday at 5:30. And we will do this problem as well. Maybe you want to try this problem and get a head start. This one is a 99% confidence interval, so that can help you as well. If you want to practice on that and then see if you're doing on the right track as you get to part 2 tomorrow. That could be an idea. Any other questions right now? I know it's a lot of information. Sometimes you just got to try these things and then see how you're feeling and see where those questions come up and then ask them the next day. Sometimes that's how it kind of works with mathematics. Questions, concerns? Practice that vocab. Get a couple other definitions if you need it. Work through it. Yeah? Okay. You're like, I'm going to wait until after the live lecture tomorrow and we will see. Okay, perfect. Thank you everyone for coming. I appreciate it. I love to see all your theoretical faces. All your names on there. It's always nice. So I will talk to you guys soon, hopefully tomorrow. If you need anything sooner, just give me a shout on email and I will try to respond. Night, everyone.